Okay, good afternoon, everyone, and welcome to the SLDS webinar. Today, our speaker is Professor Susan Murphy from Harvard University. Susan doesn't need introduction at all, but let's still introduce her anyways. Susan is a Mallinckrodt Professor of Statistics and Computer Science and Associate Faculty at the Kempner Institute at Harvard University. Her research focuses on improving sequential decision-making via the development of online real-time reinforcement learning algorithms. Her lab is involved in multiple deployments of these algorithms in digital health. She's a 2013 MacArthur Fellow, a member of the U.S. National Academy of Science, and also U.S. National Academy of Medicine. She is a fellow of the College on Problems in Drug Dependence, past president of Institute of Mathematical Statistics, and past president of the Bernoulli Society and a former editor of the Annals of Statistics. Without further ado, let's welcome Susan.
Thanks so much. It's great. It's great to be here with you. I assume you see the title page. And what I'm going to do is I'm going to talk to you about this work that was led by my postdoc, Xiping Xu. Anything I say that's not quite right, it's my fault. If I say anything really good, it's his. Okay? Our lab is involved in a number of deployments of these reinforcement learning algorithms, and that's why I put those icons on the title page. We actually just finished the first deployment of oralytics, and we're getting ready to go into a second deployment that'll start within the next couple of months. MyWays is for people using too much cannabis, and they're trying to cut back. That deployment was completed. HeartSteps, we're now on our 5th deployment, and that will go in probably next summer, almost a year from now. So we're at the very beginning of redesigning the algorithm. What I'm going to talk to you about today is ADAPTS HCT, and that's the icon on the bottom left. And this one, we'll first deploy it in a small study, and then there we'll be able to see how there's a lot of feasibility, acceptability type criteria that have to be satisfied, both in terms of the intervention content as well as the performance of the algorithm. But today I'm going to describe what we've done, where we are in terms of that algorithm at this point in time. These types of initiatives do involve a number of scientists. Xiping is off on the top right, but then there's a number of behavioral scientists, there's an oncologist, there's a guy from industry who does how the user experiences an intervention, just that face, and then there's software engineers that are involved as well, and then our team is the RL, the reinforcement learning team. So I'm going to talk just really briefly about personalization and why one might think about using reinforcement learning or RL, and then I'll go on to the dyadic setting, and I'll talk to you about this particular study, and then our first steps towards a solution. So what do we mean by personalization? So this is a digital intervention, and as you're going to see, there's a whole sequence of decisions about intervention content that get made on each individual. This particular study lasts 100 days, and there'll be a decision twice a day, every single day for every individual. And that decision is made by a policy. This policy inputs the individual state and outputs whether to provide or what type of digital support to provide. And what do we mean by personalization? What we mean is every time you deploy this digital intervention, so normally a deployment is to a set of individuals, a group of individuals. Often, and for my lab, it's often a clinical trial, but it doesn't have to be a clinical trial. In each deployment, you optimize, the algorithm optimizes the policy to enhance the effectiveness of the digital intervention. And why would you even think about doing that? You'd think you could just build a policy that is this policy that inputs state and outputs whether to provide and what kind of intervention content to provide. You'd think you could just learn that and then just deploy the policy. The problem is this is an area in which technology is changing just really rapidly. So even if there's no RL algorithm at all, you always have to, even the code gets stale after so many months, like 4 months. So society's changing very rapidly. The kinds of interventions that people could make use of, in addition to what you're providing, the digital intervention is providing, that's changing. Technology, this is where things are really going fast. We may not even have access to the same sensors in the next deployment, or the operating systems on the smart devices may have changed. All of this is changing. So with it, and also there's slight changes in the population as well because of the societal changes. So at the end of the day, personalization, optimization has to occur in every deployment. And that's what that very last line says. Personalization involves learning, improving the policy as individuals experience the digital intervention. So that happens in every deployment. So why would we want to use reinforcement learning to accomplish that personalization, i.e. Updating or optimizing the policy? Just to keep our notation straight, the state is usually denoted in this field by S. So this is the state at time t, the action at time t. Actually, in this talk, we'll only have binary actions, whether or not to send content versus not. But in many of these studies, there's multiple types of content. And then there's something called, so we have state action. The state is the state of the individual. The action is something the algorithm selects, whether, in our case, whether to send a particular type of content to the individual. And then the reward, what's the reward? The reward is what's given to the algorithm for making good actions, for selecting good actions. And it's normally constructed using some outcome related to the individual's behavior. And we'll see this later. So online RL, what does it do? So what we're talking about when we say personalization, we're talking about using an online algorithm. It inputs streaming data from individuals in that particular deployment, and it updates that policy it's using to select actions. And you can think about this as you're learning how to treat the group of individuals that are in this particular deployment. And you can see that little graph off to the right, where this would be within a deployment. You have the action, different actions are selected for different people. It just depends on their state, right? What the current policy is. And then each person provides some aspect of their behavior is the reward, and that's provided back to the agent, the RL agent, and then so on. It's really important to realize that in this way of thinking, the algorithm itself is part of the intervention. This is not part of an experimental design. This is not adaptive trial design, which is really a very powerful experimental design. But that's not what this is. This is the algorithm now is part of the intervention, and it's used in every deployment, but ends up getting updated between deployments. The algorithm itself gets updated between deployments. Within a deployment, the algorithm optimizes that policy or updates the policy. So updating of the policy goes on within the deployment, but the whole algorithm can be updated between deployments, often because the sensors have changed or the software available on the smart device has changed. Okay, so now I'm going to talk to you about this social setting, I think this is a really interesting setting. There are cases of reinforcement learning being used on social networks, but it's in a very different type of study. And I haven't seen this use of reinforcement learning. So what we have is, in our setting, we work in health, and there's a target person who has some chronic disorder, some illness that they're really having trouble with. And the behaviors or the health of that individual, that's the goal. That everything is about that individual. However, that individual is nested within a social network. And we know from the science, the behavioral science, social science, tells us that the supportiveness of that network is really critical often for helping the target person change their behaviors, or like if they're addicted, to reduce their use of substances and so on. So the study we're going to talk about, ADAPTS HCT, will have many social networks, and each one is around a little a target person, a person that we're trying to help. And in fact, our social networks are very small. They're only dyads. And but we're going in this direction. The dyad already, though, there's a lot of challenges, and you'll see that today. Okay, you can see where the interventions could come up, but let's go to the dyad. I think that's more interesting. Okay, so a dyad is a social network with only two individuals. And that turns out to be the case, at least to the first order, with the setting I'm going to talk about today, ADAPTS HCT. So there's normally, these are young adults, and there's a care partner. So you see the target person is the young adult. The care partner is either a parent or a spouse. And then there's the relationship, which you can imagine is the edge between the two nodes in the social network. And of course, the idea is to not only directly help the person achieve whatever behavior goals they have, but also to improve their relationship so that they are experience an environment in which they're better able to achieve those goals. So you can see there can be an intervention at the care partner. In our setting, that's going to be really important. This is a horrendous illness. The situation is really bad, and sometimes the care partners get PTSD. Then you have interventions at the target person. We'll see that. And then you have interventions to try and help them improve their relationship. Often the relationship is pretty stressful because they've been in such a stressful setting. And here you're going to see the example. Let me go to the next one. Okay, so this is about adolescent and young adults. So let's just think around 20. So the picture's not quite accurate. It's a little older person. And the person had to have a blood and bone marrow transplant. That essentially means you're brought to the brink of death. And then what happens is for the next 100 days, the target person, this AYA, the adolescent young adult, has to take a cocktail of drugs, and there's no positive, they don't feel better when they take the drugs. They have to take them twice a day, in the morning and the evening, and the only feedback loop that they perceive is side effects. And they really need to do this at full dose for 100 days in order to prevent severe graft versus host disease and high chance of death. So it's a really critical time. And then they also have a care partner, often a parent, and the care partner, because the adolescent young adult has come near to death, the care partner often is taking care of a lot of their needs, like they're making sure they take their medication and so on. So it's a very difficult situation. Okay, so what's the goal here is to enhance the ability of this AYA, this adolescent young adult, to adhere to their medications twice daily, in which there's no positive immediate feedback loop. Once the 100 days is over, they'll be able to reduce the dose and the side effects improve. But they need to go full dose for the 100 days. So again, as I mentioned earlier, we're going to focus on whether or not you send a particular type of support versus not. So, okay, so you see the three icons here on the right-hand side of the slide. And so the adolescent young adult, these messages, they can occur twice a day, and they're about trying to get your motivation up, trying to keep your mind on the target. You know, you're going to make it. You just got to keep going. And it has this positive psychology aspect to it. You know, you just got to keep going. Of course, the intervention content is developed by scientists, not by us. And then the icon at the very bottom is the care partner. And these are the people that are under enormous duress. They're experiencing a great deal of stress. And they could, once a day, they're receiving different tips about how to manage their stress and try and have a positive view of life. Appreciate the fact that their AYA is still alive, you know, so that could be once a day. And whether or not you send a message or not. And then the middle icon is about the relationship quality. And there, the idea is to try and promote a bidirectional relationship. And there's different activities that might be offered to the pair that would help them have a more bidirectional relationship instead of just the care partner always taking care of the young adult. So 3 different types of content. So I just went back through the RL agent again, just to give you some feeling for what the state is, what the reward is. So the action space, that's off all on the right. Twice a day, potentially the young adult could get messages related to try and keep going on, keep their spirits up, stay motivated. Once a day in the morning, tips for managing your stress if you're the care partner. And then each week, that dyad could be offered these activities to enhance their relationship. Now, it's got to be understood that all of these have burden associated with it, because these people are trying to go about their life. The young adult's pretty ill. So you don't really want to send these messages willy-nilly. They'll just check out. They'll be gone. And that's why there's the idea of a policy. You really want to send these types of messages when they are effective and not send them when they're not. And that's related, hopefully, to the state. You can see a list on the left-hand side of potential state variables. There's a lot more state variables, but I'm going to ignore the vast majority here, just so that I can try to be clear. The goal, of course, in this particular setting is indeed getting the highest adherence, twice daily adherence over the 100 days. So that's why I say the goal is maximize cumulative rewards, that is, maximize adherence. And you want an algorithm that learns as quick as it can. In other words, when I say that, by that I mean it's trying to update a policy for in what states is it worthwhile to send the messages, and when should it not bother either the young adult, the care partner, or not even offer activities because everything's just too stressful right now. There's a lot of challenges in this setting. The data is pretty limited. You only have 100 days per dyad. Because this is not a very controlled setting, you know, people are living their lives, they're at home. The noise level in all of the outcomes it's pretty high. And there's a lot of response heterogeneity. I mean, one dyad is not the same as another dyad. In particular, so the challenges I gave you on the last slide, they're kind of common to the digital intervention space. But in this case of dyads, there's additional challenges. First of all, you have multiple interventions. We saw 3. one to the care partner, one to the target person, and one to try and improve their relationship. So it makes for a complex policy. And they're going on at different time scales. So the relationship activities are more often, in this case, they're rarely, just once a week, whereas the other types of content is either daily or twice daily. Also, by design, some of the different types of actions, interventions, are intended to change the environment that the young adult is living in, as opposed to directly impacting their adherence. And this already hints that there's some causal thinking going on the part of the intervention developer. So like if you think about, it's particularly bad when you think from the point of view of content to help the care partner manage their distress. So you can see on the left, I'm looking at the very bottom of the slide. On the left, there's messages. These are these positive psychology messages. They're related to tips for managing stress. They're hopefully going to help that person manage their distress, keep it tamped down, have a more positive attitude. That hopefully will produce a better relationship between them and the target person, which will then lead to better adherence. Notice very long causal chain. I mean, this is really hard. Okay. Anyway, so this is not unusual in these settings. Given all these challenges, what have we been? We've been pretty much pushed in this direction. And the direction we're being pushed towards is we have to incorporate domain expertise. We can't, this is not a usual machine learning type setup where you have a lot of data and you can hopefully avoid expertise. We don't have a lot of data. We have a small amount of data on which to personalize. And not only that, the rewards themselves in some sense are sparse because they're about the adolescent, the young adult, as opposed to the care partner. So, okay, so how do people, when you, once you have a lot of contact with people in this field, you realize that the person who's developing this intervention, in their head, they have a whole causal chain. And like those three different types of interventions, one to the care partner, one to the target person, and one about their relationship, in the mind of the intervention developer, they're thinking each one is following a different causal pathway to improve adherence. It's quite interesting. Yet we don't really, in general, we don't even think about using that information. But perhaps that information could be used so that we can learn faster. So how are we thinking about that? So in reality, we all know that, real world causal relationships are likely extremely complex. I mean, there's probably arrows between all the variables. So the way people work together about this is they think, well, which causal pathways are most likely detectable given the noise and the amount of data you're going to have. So you realize that there are multiple pathways you're going to ignore, but the idea is they're thinking, well, those are the ones that I'm going to be much less likely to detect. So, and so this is all encoded in these directed acyclic graphs. And what we do as the data scientists is we can use these causal pathways to help to build an algorithm which optimizes the policy more quickly. Let me see, I wanted to say something. There's really a lot of bias versus variance trade-off going on because these DAGs are never going to be quite right. So I just wanted to show you one. This is just about the young adult. That's it. The R's are rewards, they're adherence. The B is a measure of burden. It's a measure of whether or not the young adult is interacting with the intervention content. A is an action. So and it's twice a day. So if you look at the subscripts, the first subscript is the week, The second subscript is the day, and the third subscript is only 1 or 2, depending if it's morning or evening. And if you look at the top row with the A's, you see there's an action, a decision to be made every morning and every evening during the entire 7 days of the week. And that square holds the entire week. Let's just look at this graph and think about what's going on, just momentarily. So we see that that action on Monday morning, I think you might be able to see my pointer. I just made my pointer. That's cool. Okay, so this is the action on Monday morning. The idea is this action, hopefully, it'll help me get my motivation up. So I'll take that drug that it's going to, remember you take these meds and you don't feel so good, right? So I'll be hopefully it'll help me take my drug, that is influence the medication adherence that morning. Unfortunately, though, by sending this notification to the individual, we do run the risk of them of interrupting them in their life, causing aggravation. So that's why there's an arrow from this morning action to B, which stands for burden. And here's the burden that sets the person up for the next time. So how does the action impact the reward? Well, the action can directly impact the reward. That is this arrow that went straight down by, I'm going to stay the task. I'll keep going. And so I'll take my medication this morning. But it can also indirectly impact the next reward because it interrupted me. Also, we know from psychology that if you apply a stimulus repeatedly, people don't see the stimulus anymore. So it's not only a burden, it's also something called habituation. They'll no longer be sensitive to these messages. So both of that's this arrow, the arrow that goes off to the right, and it goes through burden to the next reward. So there's 2 pathways going on here. And okay, so here I wrote them in black at the top of the screen on the right. We see there's 2 ways in which the action can impact the reward. It can have immediate impact that morning, but it can also impact that evening's reward by either being given at the right time, in which case it won't increase the burden, or it'll allow a decrease of burden, and then influence the responsivity in the evening, adherence in the evening. Okay, so this is really small, but I figure you guys, you're on a computer so you can see it. So what I did was I have the exact same figure at the top, but there's another figure at the bottom, and that's about the care partner. And it's almost identical, it's just only once a day. And I just want to mention a lot of the state is left off of here, because there's all kinds of things going on, like how ill the person feels that day, but we're just leaving that off for clarity here. But pretty much it's the same story for the caregiver. Here, Y is caregiver distress. So the whole idea, of course, is to try and help the caregiver manage their distress. So here's the relationship. It's in between. And it's really interesting. So this is the graph that the team came up with. Again, there's probably a lot of arrows here that are omitted. But these are the arrows that one hopes that or believes that might be detectable given the way the content of the intervention was designed. So it's very interesting to notice that the relationship is sort of is right in the middle. And so the idea, the conceptual understanding here is that by reducing caregiver distress, the way you impact adherence is by improving the relationship. And thus, you impact adherence for the young adult. So that's why this relationship, it sits in between the 2. Okay. So what is our task? Our task is to build a sample efficient RL algorithm. And when people say sample efficient, what they really mean is they're trying to learn with less data, or with rewards that are more sparse. From the viewpoint of the caregiver, the rewards are really sparse because you have to go down this entire causal chain to adherence. And so that's what I mean by the need for sample efficient. We're going to use knowledge encoded by the team. And as I said earlier, this is not uncommon in this world. Actually, the intervention content is developed with a DAG in mind. And of course, we're going to be trading bias and variance because these graphs are not quite right. But often, getting a little bias will reduce the variance so much you get a better policy, a more effective policy. Okay, so I put in light gray the adolescent part because we already talked about that. And I thought we'd just talk about the game intervention. We're going to ignore the care partner right now. So I just wanted you to practice again or to think about this because I personally find this, it's challenging, at least because I'm mixing both RL and DAGs. Which are both interesting areas, but require different, they're different skills. Anyway, so I just want to talk to you about the game intervention. So how can the game intervention impact adherence by the young adult? Okay, so AREL, this is whether or not that week certain planning for relationship type building activities is provided support for that or not. And Y is the quality of that relationship. It's really the quality of the relationship as perceived by the two individuals. So you see, so we're talking about the A with super relationship. So here you see, okay, what are the pathways whereby providing support for relationship building activities might influence adherence? So we see one way, okay, here's the action at the beginning of the week. Let's go and look at that blue arrow going up to the young adult. It incurs burden. These relationship activities, they take time. It's going to incur burden. It's a big ask of the young adult. Oh, and then if you have burden, of course, we know the burdens it's thought that will influence whether or not the person is more likely to adhere, to keep their spirits up so that they actually take the medication cocktail in the morning and the evening. So that's the reason why we have this first arrow. And notice how the subscripts are not D and T for day and time of day. They're stars because this relationship building, it's for a whole week. So it's burden over the entire week. It's AYA adherence over the entire week. That's the reason why the stars are there. So what's another way in which the relationship, so this is not a very pleasant way because this path is all about making things worse. So the second one is, so I'll put my arrow here on the second one. The second one is, it's about the intended positive effects when the intervention designer was developing these relationship activities. And the idea is, okay, so let's go back here. If you're provided these activities, you see the green arrow going to the relationship at the quality of the relationship at the next time. But what does the quality of the relationship at any given time do? It impacts the next week's adherence. That's the thought here. So that's the reason why, if you look, you see this is W plus 1. And then it's adherence over the next week. So it's this slow, it's something that builds very slowly, and you can't expect an immediate impact. That's the thought. Instead, you improve the relationship, and then in future, it's easier for the person, the young adult, to stay on task and take the drugs. That's the way the intervention designer is thinking, at least as encoded by this graph. So there's two pathways. There's the second pathway is a positive pathway, but it's extremely delayed. The first pathway is delayed, but not as bad. Yeah. And there's a similar story with the care partner, which I won't, I'm not going to go into. So So like, let's say you come at this and you've been working in reinforcement learning, maybe in ads. I have a lot of friends who work in that area. And the natural thing to do is to have one algorithm. It's going to make all the decisions. So it's going to make decisions twice a day, but on Sunday night, it's going to also have to make a decision about whether or not relationship building activities are going to be offered, support for planning. And every morning, it's going to have to make two decisions, one about trying to help the target person and who's the young adult, and the other about trying to help the caregiver manage their distress. So this agent, this one RL algorithm, is going to make multiple types of actions or combinations of actions at particular times. And it ends up making a decision twice a day, but on Sunday evening, it has to make two types of decisions. So if each decision is binary, you actually end up with 4 decisions, right? Okay, so what's the issue with one, like if I just go to it like I'm a regular RL designer, this doesn't, it doesn't account for the fact that the whole way this intervention content was developed was using these mediational pathways. It doesn't use that at all. So it's not going to get any kind of gain in terms of bias versus variance from that, at least from that perspective. If you get more nodes, which is where we're going to go, then the action space just, it's exponentially grows in the number of intervention decisions that have to be made at any time. So you go from 2 to 4, for example. Or if you have to make 3 decisions at one time, you go from 2 options to 8 options. So it's, and perhaps most importantly, the policy that gets learned is pretty complex, and it's very difficult for the domain scientists to reason about and think about. So for interpretability reasons alone, you might not want to go for one RL agent. A big advantage, though, of one RL agent is it's on task. It has one reward, it's adherence by the young adult, and that's all it cares about. So it stays on task. Okay. So what we're going to do is instead of doing that, we want to take advantage. We want to learn faster because we know we're in a sparse data, sparse reward setting. So we're developing right now for this study a multi-agent RL algorithm. So what does that mean? That means that in this particular case, there's an agent for each of the 3 types of decisions. There's an agent for the young adult, that's in red. There's an agent that makes decisions about offering support for relationship building activities, that's in green. And there's an agent that deals with the caregiver, care partner, that's in blue. This way of thinking is going to take advantage of the fact that the relationship is a bottleneck. So the impact of any intervention on the care partner only improves their relationship and thus provides support to the individual. I mean, at least that's the way people are thinking. So at the bottom of the slide, just to summarize, you see the 3 different types of agents. One agent is just going to focus on making decisions for the twice a daily for the young adult. The care partner agent is going to just focus on making decisions once daily in the morning for the caregiver. And the relationship agent is going to focus on the weekly. Okay, so what kind of algorithm, this is a pretty dense slide. What kind of algorithm are we using? What we're doing is, as you all know, if you have a background in biostatistics, biostatisticians invented the Thompson sampling algorithm. It's one of the most widely used RL algorithms in the world. And we statisticians invented it. So there's a generalization of the Thompson sampling. It's very approximate, but it's extremely stable. And it's called RLSVI. So that's what we're talking about here. So there's some facts one has to be aware of when you think of this algorithm this generalization of Thompson sampling to a setting in which you have multiple decisions, not just one decision per person, but multiple decisions for that same person. And it has to do with this notion of a Q function. And that's where the facts are. So the Q function is the expected sum of rewards into the future. You can see that it's discounted by gamma. Gamma is the discount rate. The higher gamma is, the more the future rewards are weighted. The lower gamma is, the more the algorithm doesn't pay attention that much to the future. And then there's this really nice relationship between Q functions, and that's the second equation that I wrote here. This is called Bellman's equation. And this is where the minute you see a conditional expectation, you know, oh, yeah, regression. So this second equation, the Bellman equation, is how it forms the essence of the algorithm. The idea is approximate the Q function by a linear model in some feature space, and then repeatedly form your dependent variable based on the fact that you want to estimate this conditional expectation of the reward plus gamma times the max over the Q function for the next, at the next state. So my dependent variable in this linear regression is going to be composed of two terms, the current reward plus gamma times the max of the other. And that's what's going on here in this algorithm. It got copied here from the paper. The y, which is the dependent variable, is always constructed. It has these two parts, and it's coming straight out of this Bellman equation, that second equation on the left-hand side, straight out of it. It's all very approximate. I mean, this is really approximations. And so it's called randomized least square value iteration. Why is it calling that? Because the Q function is called a state action value function. And what this does, this algorithm does, is the Q function is a random quantity. And why is it a random quantity? It's because as time goes on, you can see my pointer, you inject temporally correlated noise into the weights, the regression coefficients in the linear approximation to the Q function. And what this does is it's approximating a posterior distribution. So if we were classical Thompson sampling, this would be a Bayesian linear regression model, and you'd be using a normal distribution to do posterior sampling. So the posterior sampling is on the far left. It says select action at a particular time with a probability. Of course, it's going to depend on all the data up to that time because you're running through approximating these Q functions. And what you do is you take your approximation, the Q function, and you choose the action which has the highest. The probability of choosing action A is the probability that it's the highest. It produces the highest Q function, approximate Q function. So it's a random. The policy that's being used is a stochastic policy. And with a certain probability, action A is chosen. And that probability is high if there's a lot of the posterior probability indicates there's a lot of evidence that action is best. That's the intuition here. So we have this stochastic policy. This is great. This helps a lot with between deployment data analyses. Also, I'm not going to go into this, but this way of thinking about it from a Bayesian point of view, it allows us to be very thoughtful about the prior, which acts as an initialization to an online algorithm. So there's this really nice connection between a Bayesian way of thinking and warm starting algorithms, and it feeds straight into that. It's quite nice. Now, of course, we're going to have 3 such agents, and we have to make a lot of decisions for these agents. How should we approximate the Q function for any given agent? What states should we use? The more states we use, variables, the more complicated that regression is going to get. We get a lot more, there's a lot more concerns about instability and so on. We have to learn a lot. The algorithm has to learn a lot more parameters. It's very hard to learn. You lose degrees of freedom all over the place. What discount rate to use? So what does the discount rate mean? I mentioned this earlier. This is how you discount future rewards, which in our case is medication adherence. If gamma is high, you you really try and pay attention to longer term rewards. If gamma's low, you only pay attention, the algorithm only tries to optimize close near time rewards. And that's why it says, how long does the agent look into the future when planning? Approximately 1/1 minus gamma. So if gamma is like 0.9, then it's 1/0.1, which is looking very far into the future. People use smaller gammas closer to 0 in very high noise settings, because it's very difficult to look into the future then, to anticipate the effect of an action into the future. There's another question that has to be dealt with, and this one is quite difficult, is whether you pool across the dyads. You pool their streaming data. And the reason why it's such a difficult issue is there's enormous heterogeneity between dyads in terms of the illness of the child, how severe the illness is, how they respond, the degree of distress. It's really all about, everything is about bias versus variance. Everything I've said here is about bias variance versus variance. How much are you going to trade it off? So I'm going to not talk about the bottom of the slide. I'm just going to talk about the agent, the one agent for the young adult. And so here these are the states. Given this very simple graph, directed acyclic graph, the one that's in red on to the right, what do you need to use as a state? Well, these are the variables that have arrows into the rewards, right? So if we're interested, let's say we're thinking about the action for the individual in the morning. So the target person in the morning, let's say the evening. So then it would be, the first term would be about, well, their adherence the prior in the morning. And you can see in the DAG why that's the case, is because there's an arrow from, we want to improve their adherence in the evening, so the adherence in the morning has an arrow into it, so that's part of the state for sure. What else is part of the state? Well, you can't include this burden because that's after the action, so you can't include that. But you do need to include the prior burden, because the prior burden influences the receptivity to the action. So that's what this second term is. That's where the second term comes in. Now, those last two variables, where do they come from? They're all read off this directed acyclic graph. And so first of all, let's look at the third one, the relationship between the two individuals. So that's all about this yellow curve coming in, the relationship to adherence during the week. That's the reason why it's there. The fourth variable is there. It's tricky. It's hard to see. So here it's saying, well, you have to pay attention to whether or not this is a week in which the system is offering relationship building activities or not. That's A with REL as a superscript. Why do we have to pay attention to this blue arrow? The blue arrow is not going to adherence. It's going to the perceptions of burden by the young adult, but it's going through all the past burden. It affects the according to this graph, it can affect the perception of burden that the individual is feeling at this time when the action is chosen. So as a result, so the blue arrow goes through a burden. And so for example, this blue arrow goes to burden, and that's this this initial burden and this middle burden, and both of those can affect the adherence. So again, one needs to do this, you got to learn how to read off parents from the graph. What's nice about having three agents is that you can really trade bias and variance off differentially between the agents. And what we did here was we said, well, look, we're going to just think of a week as the horizon. So that means we're looking into the future 14 time points for the twice daily intervention. For the care partner, we're looking into the future 7 time points. And for the relationship agent, which is weekly, it's a bandit. It's just a bandit. It's a Thompson sampling bandit algorithm. It's a contextual bandit, of course, because it has a state. So all of the agents have different horizons. Now, of course, in reality, you would like their horizon to be all of 100 days, but the bias versus variance trade-off is not in your favor in that regard. So I just want to point out something that's when you start thinking about, well, these decisions, okay, you and we just decided, or at least I decided, the relationship agent is like a Thompson sampling agent. It's not going to look into the future. It's going to just look 1 week at a time. The thing you should come back to me with is this is a disaster. Why is it a disaster? Because this is the green agent. Its actions they don't directly influence the rewards for that current week. They, at least not positively, because they influence this action here. It influences the relationship, and the relationship influences the effectiveness in the following week. It sets up the environment for the following week. So this is a disaster because we're discounting, we're producing an algorithm that ignores the following week. It's a disaster, right? So you got to deal with this. We used a small gamma, i.e. gamma equals 0, to get rid of a lot of the learning variance, but we messed up because now we have no way to anticipate the positive effects of having this particular relationship building action. So what we do, and we're doing for this study, is we build a surrogate reward. And these surrogate rewards are based on mediators. So this is very interesting. I don't really see this often in RL. So I just want to point this out. So let's go back. Let's look at our red graph again, just to check it out. The red graph, we have an action A in the morning. It may impact your perception of burden by the end of the day, which may impact your how responsive you are, how adherent you are in the evening. Usual RL ignores this second pathway, the pathway from action to future burden to reward. It just completely ignores that. It ignores this mediational pathway. But if you're trying to reduce noise, it might be useful to utilize that. And that's what this is all about. So that's why the second bullet point is saying identify the mediators, because the whole game is to produce a reward which is not that noisy and also allows the agent to see a little bit further into the future. So here's our relationship agent. It has 3 mediators. We talked about that already on a prior slide. It has first, it's hopefully the relationship agent will improve, impacts the relationship, and thus in the next week will impact adherence. It also can cause a lot of burden on the child. That's this middle one. And it can cause prior burden on that child, which influences that child's adherence at the end of the week. So all 3 of these variables are mediators, and that again is read off the directed acyclic graph. So what we do is we fit a linear regression to the sum of the rewards in the week given these 3 variables. In future, it's going to have other state variables, but these are the critical ones because these are the mediators. And notice that, for example, YWREL, that's this is all post-treatment, right? So we're just constructing a reward right now. So we fit a conditional expectation. This denoises is going to have, if it's done well, it should have a lower variance. The estimated conditional expectation should have lower variance. And we use a surrogate reward for the middle agent. And it's a surrogate for predicting the current week's summer reward and predicting the next week's summer reward. Why do we want to predict the next week's summer reward? Because we know the next week's summer reward is the only way a positive effect of this intervention will ever show up. So how does this work in real life? What happens is every time before we go into the field, I'm quite the engineer nowadays, we build a digital twin of the target population. And we build multiple variants of the digital twin. These variants express concerns about arrows in the graph that we didn't use, for example. So incorrectness of the DAG are often represented by some of the variants. And it's always based on the prior deployment's data, and it replicates a lot of the noise. And we look for an algorithm with a particular discount rate and so on, which performs well across all the variants of the digital twin variants. After the deployment, we have to rebuild the digital twin again. So I just want to show you a result. So here we had 3 options. One is the orange one, which is just using the multiple agents and letting them just go after adherence. So it's not doing any reward engineering. The other is the second one, which is kind of green, kind of a light green. That's where we use these surrogate rewards. And then the third one is the one you would use if you didn't want to use the DAG, you want to just leave that out of your life. And so what we see is the cumulative adherence as the DAGs the dyads come into the study. How does the adherence get better? In other words, this is a signal of how the policy is improving over time. And you see that certainly the flattened agent is not doing well. And the real reason is it's just got too many parameters you have to estimate. There's so much noise, the algorithm it's not doing a good job trading bias and variance. That's really the only reason. It's not that it's not a good agent. It's just it needs a lot more data to learn in this type of a setting. And it's not getting that. The other 2 agents, the multiple agents, they work much better. And there is a slight advantage to using a surrogate reward. We have to investigate that more. I think we're going to have to rebuild the surrogate reward again. But nonetheless, there's a slight advantage. Here's my last slide. So this QR code, this appeared in, is going to appear in AMY, the Artificial Intelligence in Medicine conference. The site is at the bottom of the slide. I'd be glad to have questions if anybody has questions.